Okay, usually when we're doing integration, just regular integration, we are integrating on an interval or a line segment. Okay, now we will integrate over a curve. Okay, so let S be a smooth curve. Okay, remember what that means, that parametrically x and y are functions of t, where x prime and y prime are continuous and not zero at the same time. On interval a, b. Okay, so the gist of this is that we have this curve, and we're going to divide it into arcs. This is pi minus 1, and this point is pi. And delta si will be the length of that arc, and that subinterval from I minus 1 to I. And down here we have delta xi. And we're going to pick any point, and we're going to call that point xi bar, yi bar. That's any point in that subinterval. Then, of course, just like with Riemann sums, we're going to add up the arcs, and that looks like this. And then we're going to take the limit as n goes to infinity, and that's going to give us the integral over the curve. And that's called the line integral of f along the curve C. All right, if f is continuous, then this is equal to the integral a to b fx of t y of t times the square root, because this is the arc length, so this part is the ds, which is the arc length, or the length of that arc. And we can find the line integral of f along the curve C with respect to x. And that's going to be a to b f of x of t y of t times x prime of t dt. And we can do it with respect to y. And that's going to be a to b f of x. Okay, and a lot of times in this section, you're going to have to parameterize parameterize a line segment. We're going to integrate along a line segment. And to do that, we let R be the position vector. Okay, suppose the line segment, this is R0 and R1, so we use position vectors to do this. We're going to say R of t is going to be 1 minus t R0 plus t R1, and t is between 1 and 0. So for an example, if you want to go from 1, negative 2 to the point negative 3, 4, and we want to get the line segment for that and parameterize it, then all we're going to have to do is say that the vector R of t, the curve, is going to be 1 minus t times the vector 1, negative 2 plus t times the vector negative 3, 4. That's 1 minus t minus 3t. So if you substitute 0 in there, you see it starts at 1, negative 2, and if you substitute 1 in there, you can see it's negative 3, 4 is where it ends. So we have x of t is 1 minus 4t, and y of t is negative 2 plus 6t. So this is the formula you will want to remember to do line segments. Okay, see more examples in the homework. Well, what is this good for? We use all of this. One of these you can use for work. If you remember, if we took a force that was not constant and we move a particle, the force moved the particle from A to B, then the work to do that was the integral from A to B f of x dx. Okay, and we also saw that work is force times the distance, or dotted with the distance, or the displacement vector. So again, suppose we're moving a particle along this arc. And we pick this point. And it's going to move in the direction of the tangent. It's a tangent vector. So as the particle moves along the arc from the point pi minus 1 to pi, the path can be approximated in the direction of t, which is the unit tangent vector at a point, let's say t I, and its length we said was delta s I. So the work done in moving a particle from pi minus 1 to pi is approximately the force at that point on the arc times, or dotted with, the displacement vector, which is this. Because this has length 1, so this vector has length delta SI, and it's in the direction of the tangent vector. So this gives us the length, this gives us the direction. And that gives us our displacement vector. Which we can rewrite as F dotted with tangent vector ds, or delta S. But then we add up all those arcs and take the limit, and we can say that the work is the integral over the curve of the force dotted with the tangent, unit tangent vector. And if the curve is given by r of t, position vector, then we can say that this work is given by this. So either way, you can represent work like this or like that, and they're the same thing. Okay, that's it.